What's going on, physics gang? Time to review Newton's laws of motion. So, let's get to it. So, there are three laws of motion from Sir Isaac Newton. First law is called the law of inertia. Now, the word inert means not doing something, so that should give you a hint here. Inertia starts with the word inert, which means not doing something. So, the first law is an object in motion remains in motion, and an object at rest will remain at rest unless acted upon by an external unbalanced force. Okay. So what that means is that an object in the middle of outer space, which like the planet Earth, we're on the surface of Earth, so we see things get messed up by Earth's gravity, pulling things onto the floor, and then we touch the floor and there's friction and things stop. The air causes friction, making things stop. But if you think about the Earth itself, right, it's floating in empty space. And there's no rockets on the Earth. It just keeps moving. And that's what we mean, is that an object in motion remains moving, period, forever, unless there's an unbalanced force. Now, we know the Earth is orbiting the sun. Why is it going in a circle? Because of gravity. That's an unbalanced force. But if you were just floating in space, wearing a spacesuit, and we throw a ball, that's it. The ball moves in a straight line forever. That's it. Okay? Now, something we have to remember is that when something is moving at constant velocity, that feels and looks the same as being at rest. So when you're sitting at a desk like I am right now, it looks like I'm staying still, but that's only because I'm moving with everything around me, including the floor and the walls and the house, because we're rotating with the Earth. Okay? This is like how if a train is moving at constant velocity, not making any turns, you sit and it feels like you're not moving. Okay? By the way, an unbalanced force means that some force causes the net force, meaning overall forces, to not be zero. If there is an unbalanced force, that will cause an object to accelerate. Okay? So that brings us back to the original word, inertia, meaning something that's moving doesn't want to change its motion. Something that's not moving doesn't want to change its motion unless there is some sort of action taken upon it. And I can go to a simulator to show that really quick. So again, this works if we make a fictional situation here where there is absolutely zero friction. That is a real thing in the middle of empty outer space, but on Earth, even with ice, there is some friction. But this program is going to say that if there's ice, there's no friction. So let's go with that. So if you notice right now, the sum of forces is zero, and the object is remaining at rest. If I apply a force, now you notice the sum of forces is 50 because there's no friction fighting back, and the object is accelerating. So if there's an unbalanced force acting on an object, then it will accelerate. And now if I stop applying a force, as long as there's no friction, which in this case there is not, this is similar to floating in outer space, the object will continue to move at constant velocity. Which means that if you are on this object, you're gonna feel like you're just sitting still. Well, you're sitting still on this object. See what I mean? That's actually has to do with Albert Einstein's theory of relativity, meaning if you're watching this girl go flying past on the crate and you're standing still, you go, oh, the girl and the crate are moving. But from her point of view, she's sitting still on the crate and you went past her. You're both correct. All right. And to get this thing to stop moving, we again would have to apply some sort of unbalanced force and cause the object to change its motion, in this case, accelerating eventually to a stop. Okay, onwards. Newton's second law. Oh, and by the way, sorry, before Newton's second law, these are impossible. So in video games and movies and stuff, people tend to forget the force has to be external. So there's a reason why you can't just take a magnet and hang another magnet in front and make a car go forward. The magnets will cancel each other out because one of the magnets is part of the car. Same reason why you can't take a fan and blow it on a sail. Again, well, this will make more sense actually after we get to Newton's third law. We'll get back to that. All right, Newton's second law is actually just a relationship. Newton's second law is stated within this equation here, actually, which is acceleration is equal to net force divided by mass. We can cross multiply that and write it as net force equals mass times acceleration. So it doesn't matter how you write it, but this is what gives us force. So it turns out that force is mass in kilograms multiplied by acceleration in meters per second squared. Therefore, a kilogram times a meter divided by second squared gives a force of 1 Newton. Again, this relationship is shown by a graph. If you were to apply a force and measure the mass of the object and then measure its acceleration, you would get a line that is constant, and the constant line gives acceleration. And this shows us that force divided by mass gives acceleration. That would be the slope of the line. Okay, and you'll note that this equation is given on the physics reference tables under the mechanics equations right there. Acceleration is net force divided by mass, but again, you can cross multiply and write it as force equals mass times acceleration. So that's literally what Newton's second law is. It's this relationship. Okay, now Newton's third law is probably one of the easiest ones to think about, which is that every action creates an equal and opposite reaction. So when one object exerts a force on a second object, the second object exerts a force back on the first one that is equal in magnitude, meaning strength, but opposite in direction. This is called an action-reaction pair. What this means is something interesting, which is that a single force cannot exist in nature. Whenever one force is generated, another force of equal magnitude and opposite in direction must be generated. So what that means is the earth is pulling down on you, right? So you have weight. You realize that according to Newton's third law, what this means is that you are actually attracting up on the earth. Okay? So there is no such thing as one force in nature. So anytime an object causes a force on another, then the other object causes a force in the other direction, equal in strength. And that brings us back to Newton's first law, which is why it says it must be an external unbalanced force that causes something to accelerate, meaning change its motion. You cannot, again, have a fan on the ship because the fan is going to blow air on the sail, right? But then the fan is also causing a push on the air back the other way, and they will cancel out. Same thing with the magnets. A magnet will attract the other magnet forward, but then this magnet's pulling back the other way. You won't move. In funny looking, in funny cartoon or comic or whatever movie things, especially back in the day, they would have somebody in a spacesuit and they would move through space by, it's humans. We think when we're floating that we're in water, right? Like swimming. You ain't swimming. If I put you a foot away, or what's your arm length, a few feet away from the emergency door to get back into a spaceship, and you have no way of pulling or pushing on anything, you're dead. You're going to run out of oxygen in your spacesuit. You can't move. All right. So there's no way to move. And in one of my favorite games of recent times, The Legend of Zelda Breath of the Wild, there is a physics thing that bothered me, but it's a video game. But Link stands on a raft and swings a korok leaf to blow air at the sail, and then you move forwards. Sorry, Link, not going to happen, bro, because his feet are touching the raft, making friction, and every time he would swing the leaf, the air would push back on him, and then he would grab the raft with his feet and pull back the other way, meaning you ain't moving. There you go. All right. Maybe we could do one quick practice problem and be done with this. So let's see. Let's make an easy one. Let's do the only thing here that requires some math is this equation. So let's say we get an object's mass and force acting on it and calculate the acceleration. That's really all we have to do. So let's try example number 1. Let's say that the mass of an object is, I don't know, 100 kilograms. Excuse my terrible handwriting. And it has a net force acting on it equal to, I don't know, 750 newtons. Let's give that a direction. By the way, forces have a direction. They are a vector. They have an arrow associated with them. Let's say west. Okay, so let's solve for the acceleration that this object would experience. So the equation is acceleration is net force divided by mass. So the acceleration would be equal to the net force, 750 newtons of force west, divided by 100 kilograms. Let me get my calc up. So what do we got? We got 750 divided by 100, and this object would accelerate at 7.5 meters per second squared. By the way, if you were to leave the units as newtons over kilograms, you would also be correct because newtons divided by kilograms is exactly the same as meters per second squared. So don't sweat that. And the acceleration would be to the west. And now we can actually add another part of this question. So let's call that 1A. What about 1B? If you are pushing on this object, applying the 750 Newton force to the west, what force do you experience? Well, if pushing on this object, I would experience, already, Newton's third law, what would we experience? If you push on this object with 750 newtons west, you would experience 750 newtons of force, excuse my terrible handwriting, east, right? If you're pushing on this thing, it pushes right back on you the other way. Okay? There you go. I'll leave it at that. Keep this nice and short.